Hi, welcome back to this video series on cryptography. In this segment, I will talk about how to design pseudo-random functions from pseudo-random generators. So more precisely, suppose we are given a generator G that takes, say, an n-bit number, okay, and gives us, say, as an output, 2 n-bit number, okay, so double length essentially. If you feed in, say, 10 bits, you will get back 20-bit number. That's nice. It's expanding our input by 2. Okay, size of 2. Okay, that's really nice. For example, if you are say you pick a number S seed, let's assume the seed is say 10-bit. What will be the output of G of S? G of S output will be a 20-bit number. So the output size of G of S will be a 20-bit number. All right. So we are given such a generator, pseudo-random generator, PRG. Our goal is to construct a pseudo-random function using this generator. This is an interesting problem from a theoretical computer science perspective, as well as a lot of practical application. So I will talk about how do we construct a PRF. PRF means pseudo-random function from PRG, pseudo-random generator. So it turned out that we can construct a tree-like structure as follows. So first we do, our goal is to construct, remember, a pseudo-random function f, say, that takes a key k as an argument and some data point that you would like to evaluate. Okay, what kind of function is that? Let's assume, for simplicity, that fk maps an n-bit number into another n-bit number. So it's length preserving function. Okay, it takes, say, 256 bit as an input and gives you a 256 bit as an output. Okay, let's also assume for simplicity that the size of k, the key size, is same as the block length n. Okay, the number of bits here. Okay, suppose if you consider AES for a moment, you don't need to know about AES at this point. Say the key size could be 128, 192, 256, and so on. In this presentation, I'm going to assume the key size is the same as the block length size. In AES, the block length size is 128. N is 128. Okay. That's an extra piece of information not necessary for this particular talk. All I'm saying is that the function fk is transforming your n-bit input into an n-bit output in such a way that it looks random, meaning it's not distinguishable from a truly random function. Okay, we talked about how to evaluate a function is a pseudo-random function or not in the previous segment. Okay, now let's pay our attention to how do we construct such a pseudo-random function using the generator as an input. Okay, one idea we could try is as follows. That's the idea that I will be talking mostly. Is we convert our say, let's assume our x is written is an n-bit number, right? x1, x2, all the way until xn, n-bit number, right? All we are going to do is repeatedly call G as follows. First, we call G and evaluate G at point K. Okay, what will happen? We call G. For us, G is a black box for a moment. It takes an n-bit number as an input and gives us 2 n-bit. So we get at this point a 2 n-bit number, right? And then what we are going to do is we are now going to make use of our x. Okay, let's say x1. We take the x1, first bit from the left, meaning the most significant bit. Let's say the most significant bit is 0. For a moment, let's say the x1 is 0. Okay. What are we going to do then is we take the first half of G of K. So let me denote this by a notation G0. G0 means the first half of the output of G of K. Okay. And next thing we are going to do is we will take this as our, no, okay, let's take a moment. What is the size of this input? This is going to be only n bit now, right? Because remember, g of k is a 2n bit number, but we are only taking the first half. That's the meaning of this 0, the left half. That means it's going to be an n bit number. Now we can call g again on this n bit number. We will get a 2n bit number. Now we will use the second bit now of our input. Say, let's say x2 is 1 for a moment. Okay, so in that case, what we will do is we will do g1 of g0 of k. Okay, so we will continue like this until we exhausted all the n bits of our input x. Okay, that's basically what we are going to do. So more generally, we can write it like this. You will be we can generalize it as follows. So this will be gx1. This will be gx2. Remember, x1, x2 are all bits, and gxn. Okay, so how many functions are we evaluating? We are evaluating g n times, because there are n bits here. Okay, and every time we evaluate g, we get a 2n bit output, but then we truncate either the first half or the next half based on the value of the current xi bit that we are dealing with. Okay, that's all. This is basically the construction that we will leverage, and we can actually visualize this in a nice way than this formula kind of style. So let's do that. So I'm going to draw a picture which will be like a tree. Hopefully it will come across to you as a tree. Let me draw it now. Excuse me. So we have a root node, which is our key k. Key k is a secret key. Nobody knows it. Okay. So what are we going to do is we first evaluate g at point k. Okay. Then we take a decision whether to select the left half of g of k or the right half of g of k, depending on the value of x. Okay. Let's take an example. Suppose our goal is to compute fk of say 0, which is in binary. Let's say we have 2-bit number, mapping 2-bit number to 2-bit number. Let's say our g only transforms a 2-bit number to a 4-bit number. Okay. So what will happen now is that we will first evaluate g0 of k, meaning we evaluate g at point k and select the first half, right? Because this is 0 here. That's the reason I'm selecting the first half, the left half. And then I take that as an input to my next round of g evaluation, and I will be selecting the first half again of that next round of g evaluation. Okay, so let's continue this for a moment, and then I'll draw a tree for you. Okay, what about this one? So first we need to evaluate g at point k, right? And take the left half of the output. That's the 0, because this is 0 here. Then I take the first, and then I take the right half of the next round. Okay, that's because there's a 1 here. Okay, so and we can quickly write this. This is easy now, hopefully. Let's evaluate this. So we will be doing g of k and select only the right half, because we have a 1 here, and then we take again g of this, but we'll take the left half because we have a 0 here. Okay, so and finally we do fk of 1 1. Okay, which is easily z1 of g1 of k. Okay, so we can actually view this as a tree now. We make a decision whether we select the first half or the right half or the left half, right? 0 means the left half, 1 means the right half of our input x, okay? So x is the input that we will use. We will evaluate, each line here means an evaluation of g, okay? You can imagine a line denotes evaluation of g, okay? On using the root node as input, okay? So k is the input to the evaluation. So g of k, it gives you a 2n-bit number, and then we take the left half or right half depending on the 0 or 1 in our x, right? So we go to another node. So what did we get so far? At this point, we got g of k 0, right? This is because our input, let's say the most significant bit of our input is 0, 0. That means we'll go here, okay? 0. And suppose we have another 0, then we go here, right? At this point, what did we evaluate? We evaluated g of 0 followed by g of 0 of k. That's all. Okay. So now the tree is emerging slowly. And what if there's a 1 here, the second scenario here, right? So this will be g of 1 followed by g of 0 of k. Okay, and so on. Now you know how to draw the remaining parts, hopefully. So you have another copy on this side with the 0 and 1, right? To fill up this and this. So the leaf nodes, how many leaf nodes will be there? There will be, if the input is from n bit to another input, and output is n bit, we'll have 2 power n leaf nodes, right? And each leaf node is basically evaluation of your function fk at a particular input x. Okay. So as I said earlier, this is fk of 0, 0, right? This leaf node denotes the value of the point 0, 0 in binary, and this one denotes fk of 0, 1, right? And this will be fk of, if you draw the tree, it will be fk of 1, 0, and this last node will be fk of 1, 1. So there are 4 nodes, and we evaluated all possibilities. Okay, we don't really store this whole tree in binary. We don't store this whole tree in memory. This will be too much, right? Because there are 2 power n nodes at the leaf level, which is a lot. If n is a 256-bit number, we cannot store this 2 power 256 leaf nodes. No computer has memory to store that many bits. So we can actually do on-the-fly evaluation, right? Because usually we are interested in evaluating the pseudo-random function f at a particular point x for a particular key k. So we can just traverse this tree at runtime without actually building this complete tree. Okay. So basically that's basically the construction that was proposed by researchers back in 1980s. So that's interesting. I will show you some beautiful constructions that they have done. There is a paper written, let me show you that paper very briefly. There's a paper written back in 1980s, how to construct random functions. So this idea that I just talked about comes from that paper. There are some notation differences that I would like to call out in case you go and read this. So here is the tree that I just shown you. They treat x on the root node as the key. On our case, we treat x as a data point and k as the tree. That's the only difference, just a small notation difference. Other than that, it's the same idea. Okay. All right, let's get into the business of now running this idea and give a demo. First, we need to construct a pseudo-random generator, right? We need a generator that takes n-bit number to a 2n-bit number. Where do we get that? So that's the first challenge we need to solve. The way I have solved it is I used, so let me now clear the drawings a little bit. So we need a generator G. Where do I get the generator from? I use the Bloom-Shoup generator, which is basically using the idea of number theory concepts. It has a built-in assumption that it's difficult to factor large numbers, and another assumption that it is difficult to test whether a number is a quadratic residue or not. I talked about quadratic residue a lot in my other series, but currently we can assume G as a black box for us. It takes an n-bit number and gives us a 2n-bit number as an output. Okay, so I will be using this BBS generator, Bloom-Shoup generator, as a black box in my demo to mainly focus on the construction of the pseudo-random function f at evaluated point x for a particular key k. Okay, that's my goal of the demo. Okay, so I'm going to use the Python program to explain to you how this idea works. Okay, so as I said earlier, all I'm doing is defining a function f which takes the key and some data x that you would like to evaluate. So a couple of things we need to clarify here. We make an assumption here: the block length is same as the key length, and the generator takes an n-bit number as an input and gives you back a 2n-bit number. Okay, that's the reason why the output length of the generator is twice the input length. And we are going to call the generator G using the seed. Okay, the seed is the key for us, right? Because that's how we map, that's how we construct a pseudo-random function from a pseudo-random generator. Okay, so we need to tell the seed, we need to initialize the seed, we need to call the generator now, which is a black box for us. I will not go into the details of how the BBS generator is actually designed by me or implemented by me. All right, so we get a bunch of random numbers here, right? That's the bits. What is the size of the bits? It will be, we can just quickly print it here. Print bits dot bit length, right? So I have initialized my key to be a 128-bit random number. So the first output should be a 256-bit. Okay. So as you can see, the Python implementation, when you measure the number of bits, it only goes by from the rightmost position to the leftmost position until it get a 1. Okay, so it's not necessarily precise. Okay, so but that should not be a problem. What I'm trying to say is that this output is basically a random output. G is going to give us some random looking output, and we can now get rid of the size of the bits. Okay, let me clear this thing. First you get a bunch of random bits, and then we are going to make use of our x to decide whether our ith bit is 1 or 0. Remember, if it is 0, we take the left half. This is the Python syntax to select the left half of our array. That becomes the seed for the next round. Otherwise, we take the right half, right? Because the bits is an array, I have to convert it into integer for my generator, because the generator takes an integer as an input in my case. So that's just a little utility converting a binary array into an integer. Okay, so once the for loop is over, we evaluated all the individual bits of the input x by either going through the left side or the right side of the output of G, right? That's the output of G is a binary array. We either select the first half or the next half or the right half, and we use that as a seed for the next round. That's exactly what I drew on the whiteboard when we constructed the tree structure. Okay, so let's now give it a try and see what happens. We're going to evaluate fk for a random key k, 128-bit random number, and we will evaluate at point x is equal to 0 first. Okay, so you get some number. Let's do that. Let's now look at some analysis. Let's do some analysis now. So we we wanted to be able to see whether the left half is chosen and the right half is chosen and so on. Let's do that. We are evaluating at point 0, right? Fk at 0, 0. Fk is 0, 0. So we should be able to see the seed and whether we are going to the left side and the right side. For that, let's reduce the size of the key and make it small so that we can easily follow the flow. Okay, so I'm going to do print this in binary first. Print bits.bin. We'll print it in binary. So we get the random output from the generator. And then I'm going, okay, let me write it here. G of seed is equal to, okay. So, and then we will be printing here the first half, left half. Let's print the left half, right? Left is equal to, I'll be doing bin of seed because my seed is an integer. And then I'll also do the same for the right. So you can see that the seed is properly used. So hopefully we get there quickly. Right, let's try this and see what happens. That was a lot. I'm going to reduce this further, the key size, to something smaller. So just to see the idea first. Okay, so here is our output of the seed, G seed. The generator was called with some seed and it gave us this output. It is now the next round is selecting the left half. Okay, so you can see here it's only picking the first half of this all the way until 1 0 0 0, and then the next round is calculated using this becomes the seed and so on, like exactly the way I talked about on my whiteboard. So we get new seed, we evaluate G at that point, and then we repeat this process, okay, until we exhausted all the bits of our keys, of our input X, which is the same size of our key size for simplicity. It need not be, but that's how I programmed it. Let's increase the key size and do some more analysis. Okay, we can get rid of these print statements. The fun part will be change the value of X and see how the generator behaves, right? Okay, so let's do this analysis now with much bigger number. 128-bit random key is generated, and we are going to evaluate at 2 points, Fk at point X equal to 0 and at point X is equal to 1. Let's see the output. Let's print Fk comma 0, right? And here it is, print Fk comma 1. All right, let's see what happens now. We should be able to see some interesting differences between these two inputs. The only difference is first evaluation was at point 0, the next evaluation is at point 1, right? That means only one bit is flipped. But look at the output, there's a remarkable difference. Flipping one bit has significant impact on the output. That's exactly the property we are looking for when we use pseudo-random functions in cryptography. Okay, the generator G itself is a black box in this demo. I have talked about Bloom-Shub generator in my other videos. So if you're interested, watch them. But we don't need to know how the generator itself is implemented for this particular demo. One thing we have to be careful is that if we fix the key, we call the function f, the output will be the same. Let me demonstrate that. What I mean by that is, suppose I fix the key, right? And I do a little loop here and run this, say, 2 times. Okay, let's see what happens now. So you can see the first time Fk of 0 is 1 3 blah blah, and then we do Fk of 1 2 9 something. But then we evaluate it again, and there is no difference between these two, right? And the same for the other one. That's because the function f itself is a deterministic function. So don't confuse deterministic function with some random meaning. Random functions are sometimes not properly understood. We think the random function means that if you call a function with a particular input, you get some random, and then if you call it again, you get some other random number. No, you get the same random number. Okay, that's the reason I want to clarify this by running it 2 times. Okay, so we don't need to run it 2 times now. We can get rid of this. Okay, let's do one more analysis and then we wrap it up. What happens if I just change the key now? Let's say I'm evaluating the point x is equal to 0, 2 different keys, using 2 different keys, right? We also want, let me call this key and then key 1 and key 2, right? Let's key 1, let's get k1. We are going to evaluate at key 1 and key 2. We would expect a significant difference in the output also, right? For the same input point, but using a different key. Let's see how that works. Yeah, you see here, significant difference in the output. The key is different, therefore the output is different. This is also another important property in cryptography we look for. Okay, this is all because of the generator. The generator is based on a one-way function, computationally secure one-way function, based on the idea of number theory concepts like factoring and quadratic ratio and so on, which we are abstracting in this presentation. For us, it's important to know that our function f is under the hood using the generator G in a smart way. It evaluates the generator for an n-bit input and gets a 2 n-bit output. And then depending on the input x, each bit of input x is used to select which portion of the output of G should be used as a next round input. Okay, that's basically the idea of this recursive tree structure that I talked about. Okay, as you can see here, I have a for loop and I'm having a seed, which the seed is changing every time the loop runs, depending on whether the ith bit of x is 0 or 1. Okay, that's basically the idea of this construction that was developed by the researchers back in 1980 in this paper, how to construct random functions. Okay, all right, that's all. Thank you very much for your attention. Hope it's useful.